Hello and I want to welcome you to a discussion on solving equations containing radicals. Okay, so for this you'll need to know squaring property of equality. If a equals b, then you can also say that a squared will equal b squared. Squaring property does not guarantee that all solutions of new equations are solutions of the original equation. Always check proposed solutions of radicals in the original equation. This is the procedure to actually go through and solve one of these. So it's important to jot these down, remember them, or look in the book. To get started, let's look at example 1. Solve the equation. We have the square root of x equals 5. Our goal is going to be to get x by itself. So we have to remember what's the opposite, or how do we get x by itself? We can get x by itself by doing the inverse operation. What's the inverse operation of doing the square root function? That's by squaring something. So square root times the square will just leave you with what's inside of the x. X equals 5 to the second power. To simplify that, x just equals 5. Or, excuse me, just 5. Okay, now we actually need to go through and check. So we'll have our original. That is 25, excuse me, I had it written first the first time. So we'll have rewriting our original equation of square root of x equals 5. And if we plug in what we got for x, which was 25, which equals 5. And if you check this, square root of 5 is 5, so 5 equals 5 is correct. That is the solution to the equation. Okay, looking at example 2, we have to think again the inverse operation of the square root to get the variable inside away would be to square both sides of the equation. That's what we do on one side, we have to do on the other. And on the left side, the square root of y plus 13 all squared will reduce this to y plus 13 equals 4 squared. Now let's simplify the right side. Y plus 13 equals 4 squared, or just 16. Now to get y by itself, subtract 13 to both sides. So we're going to be left with y equals 16 minus 13, or just 3. So now to do our check, we rewrite our original equation, square root of y plus 13 equals 4. Now, on the second step, let's replace what we got for y. So we have 3 plus 13 equals 14. And remember, this left side is under the radical. 3 plus 13 is 16. Square root of 16 equals 4. So that is 4 equals 4. That is a true statement. And actually, this one should not be right there. Okay, looking at example 3, we have 5 square root of x plus 8 equals 13. Okay, so we don't want to start off by doing the square root right away because not a whole term is set aside with it. What we actually want to do first is subtract 8 to both sides of the equation. When we do that, we're going to be left with 5 square root of x equals 13 minus 8 leaves you with 5. Now to get the x farther away from everything else, we're going to divide everything by 5. So we're left with the square root of x equals 5 over 5, or just 1. Finally, whenever we can use our property to get the square root away by squaring both sides of the equation. When we do that on the left side, we're going to be left with x equals, and 1 squared is just 1. Okay, now we want to apply the check. By first rewriting our equation. then replacing what we actually got in for the value of x, which was 1. So we have 5 square root of 1 plus 8 equals 13. 5 square root of 1 is just 5 times 1 plus 8 equals 13. 5 plus 8 equals 13 on the next line, and finally 13 equals 13 is a true statement, so x does equal 1. Check our time. We're still doing okay. So looking at example 4, what we actually want to do is to free both sides of the equation from these square roots by squaring both sides. When we do that, we're just going to get the stuff that's left inside, because those are inverse operations of each other. So we're just going to be left with 3y plus 3 equals 2y plus 11. So now we can start getting all the y's on one side and all the regular numbers on the other. To do that, I would first subtract 2y on both sides of the equation. 3y minus 2y just leaves you with y, or just 1y. So y plus 3 equals 11. Okay, now I would subtract 3 on both sides of the equation. So you're left with y equals 11 minus 3, or that can be looked at as x equals 8. Okay, now let's apply a check. Okay, so let's rewrite our original equation of square root of 3y plus 3 is equal to the square root of 2y plus 11. Now let's replace the variables in the next step with 8, because that's what we got as a solution. So we have 3 times 8 plus 3. All under the radical equals the square root of 2 times 8 plus 1. Now let's simplify. 3 times 8 plus 3 is 27. So we have 27 in the radical. And then if we have on the other side 2 times 8 is 16 plus 20 plus 1 is 17. Okay, and if you look, this is 1, this is 11, not 1, so this is actually 27 in the radical. So this is a true statement, it checks. So that shows you that the solution is y equals 8. Looking at our next example, we have quite a bit under the radical. So let's free stuff by squaring both sides of the equation. And that will leave us with everything that's on the left side as 49x squared plus 3y minus 12 equals 7x squared. Now on the next line, let's just simplify. So we have 49x squared plus 3x minus 12 equals, and if we square this, we're going to be left with 49x squared. Okay, now if we were to subtract the 49x squared on both sides, you'll see that these will cancel out, leaving you with just 3x minus 12 equals 0. So to start getting stuff away from the x, we need to add 12 on both sides. That will leave you with 3y equals 12. Now to get x completely by itself, divide both sides by 3, leaving you with just x equals 4. Now to apply the check, we want to rewrite our original equation. And we're just going to replace every x that we see in the problem with a 4. So we have the square root of 49 times 4 squared plus 3 times 4 minus 12 equals 7 times 4. Okay, on the left side of the equation, you're going to see that that's going to amount to the square root of 784, and on the right side it's going to be equal to 28 because 78 times 4 is 28. Okay, and it turns out 784 is a perfect square of 28, so 28 equals 28. That's a true statement, meaning that 4 is a solution to the problem set. Okay, and finally, let's conclude the video with this example, number 6. So the variable is inside the square root function. So first we need to subtract on both sides to start getting stuff away from that area of the problem. We're going to be left with the square root of x plus 7 equals 10 minus 1 is 11. Okay, now we can square root both sides because it is the inverse operation of square root. And when we do that, we're going to be left on the left side of the equation of x plus 7 because that was what was inside the square root at the time. And we're going to be left with, on the right side, 11 squared. To simplify it further, we have x plus 7 equals 11 squared, or just 121. Now to finally get x by itself, subtract 7 on both sides of the equation, leaving you with just x equals, I'm sorry, I need to apologize, this is actually a 9, not 11. I added 1 instead of subtracting 1, so that we're actually dealing with 9 in there, so this should be 81. And 81 minus 7 is 74. And finally, if we apply the check, square root of x plus 7 plus 1 equals 10. We'll fill in 74 for x. We'll have the square root of 74 plus 7 outside the radical plus 1 equals 10. So inside we have the square root of 81 plus 1 equals 10. Square root of 81 is 9 plus 1 equals 10. And of course 10 equals 10, making this a true statement, meaning that 74 does equal x.